what we are going to do is we are going to take some examples of mechanical similarity. Mechanical similarity in the context that we are going to use additive property. Additive property that if there is some property which is part of the whole system, that property can be taken individually as the subsystems of that way. Okay. अब ये है कि for example if you multiply by Lagrange, multiply Lagrange means what? So Lagrangian is basically total energy of the system. So if you impose a property on the total system, that property can be imposed by its constituent parts. Got the point? This is what I said. F of x and x is x1 plus x2. F of x, this property is going to be, for example number, it's going to be multiplied with 3. 3 is multiplied by the subsystems also. Now if you take for example any homogeneous function, you might have studied differential equations. ठीक है, अगर हम कोई भी homogeneous function लेंगे, if you take any homogeneous function of the form like this, alpha or so on, where alpha is a constant, where alpha is a, so you can take it as outside. You can take this alpha outside this entire function, and you can write it as also or and maybe we can write it as a and k are the degrees of the homogeneity of the function. So if you assume it like this, that we are taking a function and it is satisfying this property, additive property is contained in this function, and if we take for example take coordinates and take time as a parameter. Coordinate means RA and time is T. So coordinates are changed by a factor of alpha. Okay, coordinates are changed by a factor of alpha. And time is also changed by a factor of beta. Time is changed by a factor of. So if it's multiplied by alpha, if they are coordinates, it is multiplied by time, it's this. But both these properties are additive. So they take the form of this function, a homogeneous function. So if it is this property, so you can say that R a coordinate can be written as alpha R and time can be taken as beta. Fine. This much is fine. Basically, we are taking that additivity, any property which is imposed on the whole system can be taken by the individual constituents of that very system. This is represented mathematically by this. Okay. And that function may be, for example, a scalar, so number. So if you multiply a whole function by that number, it's taken by the individual parts. So it's not, it's a property, it is not a property, इसमें मैं emphasize करूँगा, this is not a property observed by all systems. This property helps us to, when we calculate the equations of motions, constants of integration. So it means if there are two systems separately, once they you combine them, after combination, you are able to retrace the parts of system from where they are started. Got my point? That's it. It's an indirect way you are getting it. So that way this property is very important. अब ये है तो जो हमारी velocity है, velocity can be written as dr a by dt. But you are imposing this r a as alpha r, p as you just see it, p as beta t. What is the point? So if you impose it that way, then so the ratio of kinetic energies will be what? Ratio of kinetic energies will be 1 by 2 m. So the ratio of these two constants will be alpha square by apart from है ना, आप ऐसे लिख सकते हैं ना, we write kinetic energy. So if you reparameterize coordinates and time variables like this, so ratio of kinetic energies can also be written as alpha square by beta square. Okay, so this much is fine. Now, and potential energy is multiplied by alpha t. Why is he saying potential energy is multiplied by alpha t? Potential energy है ना mg x या h ut. So it's only time position coordinate is involved. So position coordinate का a, you can have this property alpha r1 r2. So you can have this. You can write it like this. You can write it as it's multiplied by alpha जितने number of parameters alpha 1, alpha 2, alpha 3, ठीक है, alpha 4, alpha and the number of things we are going to take k as a value. अगर ऐसे है, then alpha and beta side at alpha square now he says, now the book is imposing some conditions. So if you impose the ratio of these constants, alpha square by beta square, side that alpha to the t. So ratio of this alpha square by beta square is kinetic energy. This is kinetic energy minus potential energy is equal to this. Potential energy. So you can write, for example, this might be equal to this minus k is equal to constant. We have represented ratio of kinetic and potential energies. Alpha in terms of coordinates and beta in terms of time coordinates. Alpha r and beta t. So, but for kinetic energy, we know kinetic energy क्या है? 1/2 mx dot square. So we have taken 2 here for kinetic energy. So kinetic minus potential energy is equal to total energy. So you can also write it as alpha square by beta square is equal to, you can write for a typical case it's equal to alpha time k. K can be taken if it's 2 value. So if he says, if he imposes this condition in a particular way, you impose alpha square by beta square is equal to k square is equal to alpha j Then तो यहाँ से बीटा किसके बराबर आएगा? बीटा विल कम आउट टू बी अल्फा स्क्वायर डिवाइडेड अल्फा और बीटा स्क्वायर। अब इसका आप यूज करो ऐसे, so it will be basically अल्फा रेज फोर ये के by 2 आएगा ऊपर, ये है 1 minus 1 by 2 k। So you can write it, beta can also be written as this. You can write beta like this. So if you write beta like this, then the result of transformation is to multiply Lagrangian by a constant factor alpha k. Now, the result of the transformation is to multiply Lagrangian by a constant factor of alpha to the power k. That is to leave the equation of motion unaltered. So to leave the equation of motion alpha unaltered, अगर इसको alpha to the power k के साथ multiply करेंगे, k की alpha k by 2 ये आ गया k minus k by 2 k by 2 1 minus k by 2. So we will put this point in the most. The intention to see. So अब ये है कि a change of all coordinates of the particles by the same vector. Now these are alpha and beta. They correspond to their basically position coordinates, and position coordinates के different values आ रहे हैं x1, x2, x3. तो ज्योमेट्रिकली अगर आप देखोगे फॉर एग्जांपल इक्वेशन ऑफ स्ट्रेट लाइन क्या है mx plus c, तो x स्क्वायर ऐसे आएगा, x2 ऐसे आएगा, ठीक है? तो they will constitute the different trajectories of those particles. You got the point? The homogeneity these these equations correspond to the different figures, different trajectories in the homogeneous part of the solution. Okay. So accordingly, we can see geometrically. So equations of motion. So I'll write equations of motion permit a series of geometrically similar chords. So geometrically, so x का आएगा लाइन x स्क्वायर आएगा पैराबोला x2 है ना, closely related curves, homologous curves. अगर आप if we take the definition of geometry, so these, if we impose this property of additivity, and take ratio of kinetic energy and potential energy in this form, alpha and beta का इस form में लेंगे, so they will get equations of motion, and those equations of motion will give trajectories of particles having different geometrical shapes, and those are closely related. It's a series of geometrically similar parts. So this point is clear. अब इसमें ये है, for example, if we take a particular path, जैसे ये वाला E prime by E, so we take it as ratio of times. T is equal to beta t. So if you take T prime is equal to T, closing beta t prime, T by T prime is equal to beta. and beta के बदले हम लिखेंगे वैल्यू अल्फा टी cos k. We'll substitute beta t by t is equal to beta. Beta के बदले लिखेंगे हम alpha to the power k. And if you make this substitution, so it will come out and we'll make this substitution. It will come out to be beta के बदले हम लिखेंगे alpha raised to 1 minus 1 by 2 into k. So it will come out to be one minus one. Yes. So you also try to do it with this. So you write alpha t and t prime in terms of beta, and beta को will write in terms of this. इस सब को लिखेंगे in terms of हमारी जो L by L length, L by L is equal to T by T, है ना? Ratio of L by T है ना velocity. So L prime by T prime क्या है? V prime. Closely जो paths होंगे. So you can also write it as this. Here L prime and L are linear dimensions of two paths or linear dimensions of two pairs. Now this is a ratio of two lengths. We can also take a ratio of two velocities, ratio of two energies, and ratio of yesterday's exercise. Two angular momentum. Two angular momentum of closely generated geometrical paths which satisfy this additive property. Okay? So we have taken for two closely related lengths. Now if we take for two closely related kinetic energies, तो हमको क्या करना है? Ratio of bx square by bx prime square. Okay? So that will come out to be. So I just did it as an exercise. So b by b prime is square है, दूसरी साइड से आएगा ये रूट आएगा तो you can see it L prime by L 1 by b. And you can do the same for ratio of energies. So you just take it as an exercise to show whether you convince yourself at your place that this is equal to this or not. The same can be taken for two angular momentums. Two angular momentums हो गए, एक का one of it is m prime and this m. So it will come out to be L by L prime by L k plus 1 plus 1 by 2. अब ये कैसे आ रहा है? You have to do this algebra यहाँ पर. Angular momentum is equal to mv r, है ना? v के बजाय आपको v by v prime क्या आएगा? And v is written in terms of ratio of alpha beta and this or okay, and we get this. अब ये जो information हमारे पास हुई है, whatever the information we have got from this taking this additive property and homogeneity of a differential equation को अगर ऐसे हम लिखेंगे, such that the constants are not multiplied, ये बाहर आ रहा है constant. They don't change the property of the subsystem. जैसे कोई भी closed system है उसकी energies है, ठीक है? And there is some property which is imposed from outside. The imposed property is going to simply add to the individual subsystems. It's going to. So this is what we have taken, and there can be different dimensions to it. Dimensions means if it's 1, 2, 3, 4, so on and so forth. For example, so we are going to write it down. There is some interesting things we might learn, but they will come interesting. in small oscillations, for example, the oscillations are small, for example, the potential energy quadratic function of 2, k का जो value है for small oscillations, k is equal to 2 find. We find the period of oscillation is independent of amplitude. Now, if you have a uniform field उसका force आएगा ऐसे, m dot और basically this is du by dr is equal to f. अगर हम ये लेंगे and k can be written as 1 from if you take I just forward by g this equation effectively. If k is equal to 1, if take k is equal to 1, तो k for k is equal to 1, q prime by 2 इसके बराबर आएगा. k y का 1 minus 1 by 2 जाएगा root of l by l. L prime. And where we will take the simplest cases of Newtonian attraction and Coulombic potential. उनका potential है ना same 1 by r square, है ना? Whether it's Newton's force or whether it's अब न्यूटन्स फोर्स में टू बॉडी प्रॉब्लम में क्या आता है, टू बॉडीज इलिप्स बनाती हैं या चार्ज पार्टिकल्स अगर प्रोटॉन और इलेक्ट्रॉन है हाउ दे सो जो उसकी इक्वेशन ऑफ मोशन है गॉट द पॉइंट द ट्रैजेक्टरी ऑफ दिस सो यू कैन इंपोज सम कंडीशंस दैट यू विल सी विल गेट फॉर एग्जांपल सो इफ न्यूटन्स टू मास if they are homogeneous functions of अगर ये k का value 1 minus 1 लेंगे, if you take the value of k, if you take value of k जो है, you see here, इसका value 1 लेंगे, ये क्या आएगा? p prime by 2 क्या आएगा इसका value? क्या आएगा इसका value? k is equal to 1 minus 1. So if you take minus 1 तो क्या आएगा ये? 1. ये आएगा 3 by 2. आएगा क्या? हाँ you see here. What will come out here? यहाँ पे k का value of 1 minus 1. So इसको 3 by 2. So it will come out. आपको यहाँ से आप निकालिए. We have got a Kepler's law की definition. कैसे Kepler's law की definition है? वहाँ है ना ratio of this time period is equal to the cube of this major action cube. It is a cube of the size of the orbit. Cube of the size of the so this is known as Kepler's law. So we'll do it again, but here the point to show is that imposing upon some simple conditions, we can arrive in simplest cases. अब ये है ना value of k what we are going to take, it depends upon जो मैंने कहा था. They are closely similar geometrical figures or trajectories. So for a particular case of k is going to minus 1, we could retract or relieve our Kepler's law, Coulomb's, Newton's law when applied to this. Okay, this. So if it's in a finite region of space and time, we'll also get something you might have studied real theorem. Real theorem है कि in limited context, in closed systems, this is a simple relationship of kinetic and potential energies of the system. Okay, we can also from this argumentation we can also arrive at the understanding of real theorem. So this is it. So again, if you want to process again this homogeneous function को अगर हम kinetic energy को in terms of 3 लिखेंगे, P is quadratic function of velocity जो आपको पता है quadratic function मतलब कैसे ये ना 1/2 mx dot square that's why it's P kinetic energy is quadratic function of velocity. So we can also write it as like this by this लिख सकते हैं कि नहीं चलो ये आ गया d by dt by d ये Lagrange है ना this Lagrange this is 1/2 mx dot square तो पहला वाला डिफरेंशिएशन क्या है ये आ गया
It's double dot.
ये
X
आ
with
गया
respect to x dot.
हाँ ये आएगा
X dot.
1/2 mx dot square है ना
Q dot.
ये q dot है ना ये x dot
Q dot is x dot. Component x dot component. Yes.
तो it will come out to be x dot और v आएगा v को मल्टीप्लाई करो v के साथ तो क्या आएगा v square है ना हाँ v square so this is another way of writing so v square 1/2 and v square 1/2 यहाँ नहीं है 2 हम यहाँ से so we can also write it as normal kinetic energy को मतलब Lagrange formula ऐसे भी लिख सकते हैं ठीक है so if you write it this way kinetic energy का form we can write it this way and further one more thing is that we can write this thing in terms of object of can we write it in terms of this way or not लिख सकते हैं कि नहीं ये ना mv ये mv square है so again can we write it like this P A V R dot R E minus हाँ लिख सकते हैं कि नहीं देखो आप the first term will have two terms sorry
Yes.
the first term will have two terms P पहला आएगा P A R D R A by D T will become back the second term जो आएगी इसकी R A P A dot that R A P A dot will cancel with this thing and we have simply rearranged it we can write this 2T also like this अब ये है कि जो ये total energy kinetic energy of the system can be also written like this ठीक है if you want to write kinetic energy in terms of Lagrange equations of Lagrange formulas अब ये करने से why do we do this exercise we want to show something important or some interesting fact comes out what is the interesting fact so what is the interesting fact ये तो Lagrange of a given function है but if it's the Lagrange of the total system Lagrange of the total system क्या हो गया means if you want to understand it's the total energy of the system अब total energy of the system we have computed in terms of VA so it is not a static thing it is something dynamic thing जैसे कोई एक पार्टिकल यहाँ से वहाँ गया वहाँ से यहाँ गया इसकी potential and current they continuously change but we are saying that the closed system के लिए it will come out to be constant it will come out to be constant so अगर आपकी Lagrangian है या kinetic energy है for a system so it will come out to be अगर हम इसका average value where we will take its average value 1 by tau average value can be taken as f of t है ना average value take x1 plus x2 plus so on is divided by x so it's average value of that wave function so we'll take a general function now we are going to take that Lagrangian of that system closed system में क्या है total energy of the system and it will come out to be अब सिंस डी आई बाई डी इसको आप इंटीग्रेट करोगे, इंटीग्रेट करके आप ये आएगा एफ टी माइनस एफ ऑफ जीरो, फंक्शन ऑफ दैट फंक्शन हैज टाइम टी एंड इट्स इनिशियल वैल्यू. तो अगर ये सिंस वी आर टेकिंग दिस थिंग एज average, it's a closed system, we can assume that it will come out to be, the average value will come out to be zero or constant, although it's an approximation, but we are assuming it that since it's a closed system, तो average की जो net energy होगी initial minus final time में, that will come out to be zero or that will come out to be some constant. अब यहाँ से इससे हम क्या कर सकते हैं? What do we get from this? Now, if we assume that the system executes a motion in finite region of space with finite velocities, then this term, so यहाँ पर हमारे पास we wrote this energy in terms of this and this. If the system is bounded, तो ये है ये वाली तरह, जो net जो derivative of this, it will come out to be zero. आई कि नहीं? Net changes जो आ गई ना, total changes average में, so it will for a bound system or for closed system, it will come out to be zero. It will come out to be ये naturally क्या आएगा ना, total So total energy of the system जो होगा average value, it will come out to be zero. So from that argumentation, d by dt of b dot d by dt is change in the momentum dot. This will come out to be for this average value of integral, it will come out to be zero. And the second term जो हमारे पास होगी, basically we are trying to write जो हमारी kinetic energy है या total energy in terms of Lagrange function कैसे लिखेंगे? We wrote इसको in terms of दो terms. First term we say that it comes out to be zero by this logic. That average energy, if you take average of the value of that function, उसका derivative without time, if you compute that integral, it will come out to be zero. And then only this term will contribute. ठीक है? So if this term will contribute, तो total energy 2T है, 2T हमारे पास है, it will come out to be can be written like this. This two. So in this. And further, जो हमारा ये है momentum है ना, momentum is basically, can you write it as ये basically ये है PA dot. This is PA dot. Basically force is equal to dP by so F dot dr है, you can also write it as F. So if it is dPA dot is dPA by dP, so that is F का दूसरा form है, F will also write F in terms of this. Okay. So if you write F in terms of this, so we can write the energy of the system for this come out to be this. And further, ये है d by dr of dr. इसका ये है. If the position coordinates are said to be some constant x1 x2 x3. तो ये है इससे कांस्टेंट r, so it will come out to then it will come out to be 2t is equal to 3 times 2t is equal to 3. So you see, so ये जो Lagrangian form है for a closed system, जो एनर्जी का फॉर्म हमारे पास आता है, it will take this form. It will take. So इसी को इस इक्वेशन को sometimes if you see in books, it's also called virial of the system. So अगर आप ये है इसका फॉर्म को है written like this. Now we are going to have some manipulation. If total energy plus this is equal to E, then we can write U as doing substitutions. We can write U as E plus and T to S. For example, in particular for small oscillation, if you take k is equal to 2, अब ये कैसे आए U and T का वैल्यू, you just manipulate these two equations. For small oscillation, जिस तरह हमने वहाँ लिया था ना, for k is equal to -1, we got the orbits of Kepler's law. ठीक है? For you have to see for k is equal to 2, what will come 3, 4, so you get different trajectories. ठीक है? इन प्रिंसिपल क्वेश्चन ये है कि नेचर में जो हमारा अर्थ मूव कर रहा है अलोंग एलिप्स है ना, अराउंड सन, तो व्हाई नॉट एनी अदर स्फेरिकल फिगर, कि व्हाई नॉट एनी अदर फिगर, फॉर एग्जांपल इज बाउंड बाय 1 बाय r 4 कूलम्ब्स लॉ है ना, 1 बाय r स्क्वायर, ग्रेविटेशन लॉ भी है, उसकी वजह से ये ट्रेजेक्टरी आ रही है ना, ये वाली ट्रेजेक्टरी आ रही है जो हम देख रहे हैं मैनिपुलेशन केस को मान. So if it had been r cube, r3, r4, would have what? Other trajectories. हम in principle we can calculate all sorts of trajectories or all sorts of neighboring paths we can calculate. तो जो हमारी problem of interest है, whether it's in small oscillations, if the particle is vibrating very small, what term you are going to take? To take higher order corrections to कौन सी वाली trajectories हमको लेनी, ठीक है? So these are given by this sort of analysis we get in roughly, ठीक है? अब इसमें आप ये है, there are very one or two interesting problems. They are unsolved. Just try to at least attempt it. Just for example, I'll read one of the problems. What you want to say? Find the ratio of times in this. Find the ratio of times in the same path of the particles having different masses. Find the ratio of times in the same path of particles. Particles का path same है. Path is same, but mass of the particle is different. Mass is different and potential energy is same. So two particles are traversing on the same path. They might be having different masses. And the potential energy is same. So अब ये कह रहा है कि इनका क्या निकालो, इनका टाइम निकालो क्या है, the ratio of 2 times t prime by t क्या है. So you just उसका argumentation system है. So you try to attempt these two problems. Once if you are able to do it yourself, it will give you some confidence. जो हमने जो आज किया ना, what we mean by homogeneous function, वो प्रॉपर्टी को यूज करते करते we arrived at different things. Taking the value of k from 1, 2, 3, -1, so you can get different trajectories of particles. ठीक है?